In this video, I will begin talking about cardinality. We will start working from finite sets and then working our way up to infinite sets with cardinality L of naught and then other cardinalities. We have to start working from the bottom up, work on our structure. The first thing I need to talk about is what it means for two sets to be equivalent. Well, two sets are equivalent if they have a one-to-one onto correspondence from one to the other. A simple example we could look at is let A equal the set 1, 2, 3 and B equal the set ABC. I can easily come up with a mapping from A to B that's clearly one-to-one and onto, so A is equivalent to B. In fact, whenever you have two finite sets that have the same number of elements, they are equivalent. It starts getting interesting when you start talking about infinite sets. So let's do that. Let E equal the set of even integers. So it's everything of the form 2k where k is an integer. While f is a mapping from z to e, I'll define to be f of k to equal 2k. Clearly one-to-one and onto. I'll let you prove it as an exercise. So the set of integers is equivalent to the set of even integers, which is kind of freaky since e is a proper subset. Let's look at another one. I'm going to define a mapping from the natural numbers to the integers. Okay, so integers. Got all the negative whole numbers and the positive whole numbers and 0. I want to find a mapping from n to z that's one-to-one and onto. Well, let's start. The first number in n is 1. I'm going to let 1 be mapped to 0. And next I have 2 and 3. 2 goes to 1, 3 goes to negative 1. Next I'm going to take 4 to 2 and 5 to negative 2. See the pattern, how I'm bouncing back and forth. I want to do that to make sure I hit every one. So by construction, this thing is going to be one-to-one and onto. So I've shown that the natural numbers are equivalent to the set of integers. The relation defined this way is an equivalence relation on the set of all sets, and I'm going to let you prove this for homework. But the gist of it is, you want to show that A is related to itself, reflexive. Well, you can use the identity function. If you have a mapping from A to B that's one-to-one and onto, F inverse goes from B to A, and it's one-to-one and onto. If you have a mapping from A to B and a mapping from B to C, the composition goes from A to C, and if they're all one-to-one and onto, the composition will be one-to-one and onto. Suppose A, B, C, and D are all sets, and A is equivalent to C and B is equivalent to D, then A cross B is equivalent to C cross D. So if A is equivalent to C and B is equivalent to D, we have something like this. F is a one-to-one mapping from A to C, and G is a mapping from B to D. I need to construct a mapping from A cross B to C cross D. Elements in A cross D look like A comma B, and elements in C cross D look like little c comma little d. I can get the A to go to C by using F, and I can get the B to go to D by doing G. So this mapping, the way I constructed it, will be one-to-one and onto. Again, I'll have a more formal proof in the write-up, but that's the gist of what we're doing here. Next, if same situation, A is equivalent to B, C, and B is equivalent to D, but if A and B are disjoint, C and D are disjoint, then I could union them and get new sets that are equivalent. So A and B have nothing in common, so I'm going to denote them with two boxes. So A stuff's over here, B stuff's over here. Same thing with C and D over there. I will let F act on A and G act on B, and they will kind of take the things in parallel to get to CD. So this mapping where you let F act on A and G act on B is the mapping we want to go from A union B to C union D. So now that we've got that, let's start with our definitions of finite sets. We need a canonical, a basic finite set. Let n sub k equal the numbers 1 through k. This is a finite set. A set is finite if it's equal to the empty set or it's equivalent to one of these n sub k's. If a set is not finite, it's infinite. Cardinality, the cardinality of the empty set is 0 because there ain't nothing in there, and the cardinality of n sub k is k. So let's start building up some theorems. If S is finite and has cardinality k, and X is some element not in S, cardinality of S union X has cardinality k plus 1. So in English, if you have k things, and grab something else, you now have k plus 1 things. Pretty much of a duh moment. But we have to prove it, and we have to prove it with some rigor. So if S is finite and has cardinality k, it's equivalent to the set n sub k. The set containing just x is equivalent to the set containing just n sub k. Bringing these two functions together, I now have something going from S union x to n sub k union k sub 1, but that's just the same as n sub k plus 1. So therefore, S union x will have cardinality k plus. Every subset of n sub k is finite. We're going to do it with n sub k first, and then we'll do it with regular old sets. So let's say I have a set, n sub k. There's my set. And I have some subset of it. Maybe this one's in there, maybe that one, maybe this one. The key is I can take this set and number them. I can say, well, that's the first one, call it a sub 1. That's the second one, a sub 2, yada, yada, yada. That's the last one, a sub r. So now that I have that, I can put S over here and say, okay, S, I'm writing it as a1, a2, yada, 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 down to a sub r. I can come up with a one-to-one onto mapping from S to n sub r by taking a sub I to I. This is clearly one-to-one and onto, so now S is equivalent to n sub r, which means it's finite. So now we have every subset of n sub k is finite. What I need now is every subset of any old finite set is finite. So let's start with a finite set, and we start with a subset of that finite set. If A is finite, there's a one-to-one onto mapping from it to n sub k for some k. Well, F is inside A, so it's going to get mapped over there too. And this is a one-to-one. When you restrict F to just B, this is still going to be one-to-one. It'll be onto because I'm only looking at F of B. I'm only looking at things that got spit out when you F'd B. I know B is equivalent to F of B. F of B is inside n sub k, which means it's finite, which means B has to be finite because they are equivalent. They must share that property. If A and B are finite sets, then A union B is finite. I'm going to assume A and B are disjoint, because if they weren't disjoint, I could force them to be disjoint by saying, okay, well, I'm going to look at A, but then throw out all the stuff from B, and then have B all by itself. So I can assume, without loss of generality, that A and B are disjoint. Now, if A is finite, it's equivalent to some n sub r. So I've got a nice one-to-one mapping from A to n sub r. If B is finite, I have a mapping to, say, n sub s for some s. I know, I mean, you can look at this and say, okay, well, if A and B is finite, A's got r things, B has s things, it's going to have r plus s things in it. So let me look at n sub r plus s, and I'll construct the mapping where everything from A will get mapped over to what it normally would have gotten to map to in n sub r. But then once you get to B, whatever went to 1 will now go to r plus 1. Whatever went to 2 will go to r plus 2. On down, S gets mapped to r plus s. So this is a one-to-one onto mapping from A union B to n sub r plus s. Therefore, they're equivalent. Therefore, it's finite. And by doing this argument, we've proven the next one. If A and B are finite disjoint sets, then A union B, the cardinality of A union B is equal to the cardinality of A plus the cardinality of B. I prove that if A and B are finite, their union is finite. I'm going to leave for you to do this one, and this is done by induction. Because I've already proven that the union of two finite sets is finite, you should not have to get into mapping and all that kind of stuff. You can just do it by induction. So this one's analogous to the one where you add 1 and the cardinality goes up by 1. This is you take 1 away and the cardinality goes down by 1. Let's say I've got n sub k, and there's some x stuck in the middle there. And I want to take that x away. And I need to find a mapping from here to n sub k minus 1. So here's my list. Now x is still here because I'm numbering them from 1 to k minus 1. So that x still needs to be in there. But since I removed 1, there's one less thing in this set on the right. So if the number is less than x, it's going to be mapped to itself. If it's greater than x, it'll get mapped to itself minus 1. So you kind of shift everything on the top down by 1. This is a one-to-one onto mapping, so the two are equivalent, which means the cardinality of n sub k minus 1 element is n sub k minus 1. Next up is the pigeonhole principle. The idea behind the pigeonhole principle is, suppose you have 5 things, but only 4 boxes, and everything has to go in some box, then some box has to have at least 2 things in it. That's another way of stating this. Doing it mathematically, I have n and r are elements of the natural numbers where n is greater than 1. If n is greater than r, and f is a mapping from n sub k to n sub r, then there's no way f can be 1 to 1. Something's going to get smushed. 2 things are going to get hit twice. So we have to do this by induction. So let's start with n equals 2, because that's the smallest it can be. And if n equals 2, the only thing r can be is 1. So let's look at what we have. There's n sub 2, there's n sub 1. If I come up with a function, well, 1 has to go somewhere, but the only place, 2 has to go someplace, and the only place it can go is 1. And 1 has to go someplace, the only place to go is 1. This is not 1 to 1. So this holds for n equal 2. Assume true for some n. And we want to prove for n plus 1. If we're proving for n plus 1, that means I'm proving this for any r less than n plus 1, which means r minus 1 is less than n. So let's say we have this situation. I have any mapping from n sub n plus 1 to n sub r, where r is less than n plus 1. If all of the stuff 1 through n goes to the stuff 1 through r minus 1, and n plus 1 is mapped to r, no problem. I know that this part cannot be 1 to 1 by our inductive hypothesis. I'm going from something from n to something less than n. This part can't be 1 to 1, so I don't care what this is doing. The problem comes if n plus 1 is going to somewhere in the middle and something in the middle is going to r. Then I can't use my inductive hypothesis. I need to wiggle it. Doing this by contradiction, I'm going to assume that f is a 1-to-1 function. I'm going to come up with another 1-to-1 function from here to n sub r, where everybody goes to themselves, except I'm going to switch these 2 things back. Whatever was in the middle is now going to r, and whatever r came from will go back to, does that make sense? This guy from nowhere hits r, so r is going to throw it back. Plus 1 went to something in the middle, and whatever that thing in the middle is going to get mapped to r. So if we look at the composition of these 2 functions, I now have something going from 1 through n to 1 through r minus 1, which by our inductive hypothesis can't be 1 to 1, so the entire composition can't be 1 to 1. So the pigeonhole principle holds. A corollary for this is a finite set is not equivalent to any of its proper subsets. This is going to be a handy theorem because we're going to be able to use this to prove something is infinite. Like we now know that the integers is infinite because it's equivalent to one of its proper subsets, and it can't be finite if it's equivalent to one of its proper subsets. Let's say we have a set A, and it's equivalent to n sub n. We have a nice, pretty subset of that, and it's equivalent to n sub r. It's a proper subset, so I know that r is less than n. If A were equivalent to B, then I could use that to create a mapping from n sub n to n sub r, and that mapping would be 1 to 1 and onto. Contradiction, we can't do that because of the pigeonhole principle. A lot of stuff to unpack in this section. Look through the proofs. We'll play with some examples in class, and we'll try not to get too bogged down in the oogie details and try to see what's fun. And I think that's a good place to stop.